Good morning, everyone. This is Ashish Gupta, NBQP Quality Council of India. I welcome all the participants to this webinar on importance of measurement system analysis and statistical process control. Before we begin with the webinar, let me give you a brief about QCI. Quality Council of India was established as an autonomous body under the Ministry of Commerce and Industry. Our nodal point in the Ministry of Commerce and Industry is the Department for Promotion of Industry and Internal Trade. QCI is driven by the dynamic leadership of our chairman, Mr. Adil Zainul Bhai, and Secretary General Dr. Ravi P. Singh. As an apex quality organization, QCI QCI has five constituent boards. First, NABC B National Accreditation Board for Certification Body. Second, NABET National Accreditation Board for Education and Training. Third, NABH National Accreditation Board for Hospital and Healthcare Providers. Fourth, NABL National Accreditation Board for Testing and Calibration Laboratories. Fifth, NBQP National Board for Quality Promotion. This program is also brought to you by NBQP. QCI also has a special project division. First, Project Planning and Implementation Division, PPID. Second is PAD, Project Analysis and Documentation Division. Third, Zero Defect, Zero Effect. Fourth, Training and Capacity Building. With its constituent board and division, QCI continuously leads its mission of nationwide quality movement. Through our webinars and trainings, we strive to enrich the understanding of the participants and also enhance quality of life in various ways. Our today's webinar is on importance of measurement system analysis and statistical process control. MSA and SPC are two likely key pillars for a manufacturing process to ensure process control so that desired quality of product and services can be achieved. MSA is defined as an experimental and mathematical method of determining the amount of variation that exists within a measurement process. Statistical process control is defined as use of statistical technique to control a process of production method. Key tools used in SPC include run chart, control chart, a focus on continuous improvement, and the design of experiments. Therefore, to learn these smart functions of MSA and SPC, I invite Mr. Amit Kumar, a graduate engineer and a certified Lean Six Sigma Black Belt professional. Amit has done various Operation Excellence projects both India and abroad through Lean Six Sigma methodology. Amit is an expert with more than 14 years of experience in delivering Lean and Six Sigma practices and project management in various sectors like manufacturing, financial, IT, ITS services, garments, etc. Involved in various project management including process of initiation, planning, execution and monitoring and controlling and closing activities to integrate them to ensure proper coordination. Amit has facilitated over 120 projects spanning different industry segments and has trained more than 1000 people in areas related to Lean Six Sigma. Amit possesses strong leadership skills and has very strong connect with business owners. I am sure you all would benefit immensely from his knowledge and wisdom. Before we move ahead, I would like to share some ground rules for the webinar. Please keep your mics on mute unless you need to ask question. This will help to prevent any distraction. The trainer will prompt you to ask questions that when you may unmute the ask question. You may even raise your hands by clicking on the icon so that your name would be announced once we open for the question. And you may also type your question in the chat box and these will be announced during Q&A session. With this, I welcome Mr. Amit Kumar and request him to enlighten us. Over to you, sir.
Yeah, thank you so much and and thanks for the lovely introduction. Yeah, give me a second. Let me share my screen, please.
Sure, sure.
Yeah, good, ma'am. Yeah. Hope my screen is visible. Yeah. Is it visible?
Yes, it is visible.
Yeah. Yeah. So, good morning, my dear participants. So today's topic is measurement system analysis and statistical process control. So before we begin, it's important to understand today's competitive business environment. So if this is our industry, we face competition from Western technology. If we talk about Western car, these Ford car and all those things, these technology. So somehow we have to compete with technology to survive in the market. And second thing, the quality of the Japan. So they believe in first time right. So quality also we somehow have to compete on day-to-day life to compete in the market. And we know about this Chinese market. They are they reduce price like anything. So when we are selling our product, whenever we are doing some manufacturing, it's important to understand how to play with these Chinese player. And at the same time, this domestic competition we can't ignore, so we have to face this also. So somehow what we have to do to survive in the market, we have to have some competitive edge over others. So this MSA and SPC is also one of the tool in lean manufacturing which help us to have that competitive edge. So before we go into technicalities of MSA and SPC, I'm sharing this photograph with you. And if I ask you, you can just do of your own. Are these horizontal lines parallel to each other? I'm giving you a few seconds to answer. You can just write yes, whether these are parallel or not. Are they looking parallel or not? Think from the perspective, we all are people who are measuring some data in an industry, and probably when I get some input from you, people can say, yeah, these lines look parallel. Somebody will say, no, no, it's not looking parallel. I hope you have the same verbatim, which I am saying. So there comes, some difference in the thought process of operator or the participant or the people who are trying to capture the data. So same thing happens in manufacturing or service. When we are capturing the data, a person is saying something different, B is saying something different, C is saying something different, and data is same, but all thought process, all the capturing approach is different. That's part of MSA. And second slide, if I say, if I ask you to look at the chart and say the color, not word, if you can just do it. This the first word, your first word is written yellow, but it's written in green. If I ask you to read quickly, so we will won't be able to read it properly. So it's because of some left and right conflict. Your right brain try to say the color, but your left brain insist on reading the word. So these all are part of my measurement system. When I am trying to capture the data, I am producing any piece and trying to capture the reading, some deviation come between the operator. That all comes under MSA. So let's start with the technicals of MSA. What this MSA is, keeping these that pictures into mind. So when I'm talking about this MSA measurement system analysis, it checks the true variation and variation due to measurement is in the system. So one, there would be a true variation which will definitely going to exist in the my measurement system, which I can't ignore. But the data I'm capturing, because of some system I am adopting, or maybe the training is not given, I am getting some different data. The captured data is different. So this my measurement system analysis is going to tell me why this difference is coming. Is it because of some operator that difference is coming, or because of something else, which we will see in coming slides today. Second, it identify and describe possible source of variation in a measurement system. So whenever we do some measurement, the first thing is what data I have captured. That is one thing. Second thing, if I have captured the data, is it correct or not? If it's correct, that's good. If it's not correct, from where that variation is coming? Because at the end of the day, we have to plug that gap. So MSA, measurement system analysis, is going to do that for us. Its method of determining the amount of variation that exists within a measurement system. So, when we are capturing the data, it also become important for us the data which we are capturing with the help of different gauges, maybe vernier caliper or any of the gauge, whether we can accept that data for our further analysis and further manufacturing or not. So whether to accept that data, or we have to reject the data and we have to somehow use a different technique for capturing. This measurement system analysis will going to tell me whether to accept data or not accept. And if I'm not accepting, then why I'm not accepting, who all are the culprit, because why I'm saying it, I'm not going to accept that. So MSA is going to tell me all those things. Describe the importance of validated measurement system. So if I am saying I am accepted my measurement system, I am taking data from my gauge, I am using my set of operators for capturing the data. So am I saying that my system, my measurement system is good enough, is fair enough for to proceed further? This MSA is going to tell. It described the term which we will discuss, the term precision, accuracy, resolution, and all those things, and to validate the measurement system before doing statistical process control. So there are two things which we are discussing today, MSA and SPC. So once we are done with MSA, when I am fair, when I am with full confidence, when I say that I am going to accept my MSA, then only we can proceed with SPC, statistical process control. And my measurement system must demonstrate these couple of things, which says whether my system is stable throughout or not. Whatever data I'm capturing, that stability my system is providing or not. The stability we will discuss in little bit detail in coming slides. And minimal variation as proportion of process variation. If my process is varying, my customer has given some tolerance to me that that my process, I can have this much plus minus 0.5 tolerance. So within, is my measurement system able to capture that tolerance? Is my measurement system strong enough for capturing those data? So in nutshell, MSA talks about these many parameters. So this is brief about MSA. So let's see, why this MSA is important, why we need to understand this, why we need to do this, what our elements are there. So to identify the true process variation, as I said, my process would be having some true variation which I can't skip, which I can only minimize, which I can't reduce further. It can only be minimized. So it's going to identify that where are those true cause of process variation. And second thing, to have reliable and trustworthy data for decision making. So my customer is saying, you make this piece and I am accepting this minus this 50 plus minus, let's say 0.5 tolerance. So I have started, and based on the customer voice, customer information, I have started making the piece in my industry and starting data also and starting doing measurement analysis. So this data, the second point is saying, so whatever data I am getting, this MSA will tell me whether that data is reliable or not. So that's why this become important to capture MSA, to have MSA for our industry, and to make better data driven decision. Because whenever we talk about any process improvement journey, which is MSA and SPC is part of it, so it all based on my data. So it helps us and to smart spot small changes in the process. If my process is deviating, so MSA is going to tell me my process is deviating, and to what degree it's deviating, whether to accept it or not. All this measurement system analysis is going to tell me. Risk of taking wrong measurement without proper measurement system. So this is going to avoid that risk, to have that wrong measurement, because MSA will tell me whether to accept that data or not. So let's have little bit deep dive what all elements are going to be involved in my MSA, because till now we talked about some generic about a measurement system analysis. Now we will have understanding what all elements are going to be involved. So when we are doing MSA, what all parameters we need to take care, what all the would be the things which could be responsible or which are responsible for MSA. So these are my first one is my procedure, which talks about the set of techniques I am using for doing and capturing my data. And second is my standard, what standard I am using to capture the data. So it's talk about what's my actual value. If I am saying this is having 10 centimeter as the true value, this is the true value, that this is its length is, let's say, 10 centimeter. Now people operator have started measuring it. So are they getting the same value? If I'm saying 10 centimeter, are they getting 10 centimeter? How close value they are getting? So it's a measurement against the standard value. And third parameter is my equipment, or I can say gauge. So the device which I am using, if I am using scale for measuring the length of the pen, so I will say and the gauge or equipment is scale. If I am using vernier caliper, then I will say my gauge is vernier caliper, or micrometer, any of the gauge. If I'm whatever gauge I am using, that will fall under my equipment and gauge. And operator, the fourth parameter is operator, which talks about the operator, the resource. We also call it appraiser in MSA language. Appraiser who is capturing the data with the help of gauge by using the set of procedure. So that will be my operator. So these four elements are part of my measurement system. So I was talking about in initial slide that the way variation comes when we do measurement of any of the part or any of the piece. So these are the broad categories why these variations are coming. So it's going to fall always within these parameters only. So if we see, the first one is my observed process variation, which further categorized into two elements. The first one is my actual process variation. So actual process variation is which is inherent in my process, which we capture through SPC. This mainly is part of SPC. It talks about the process capability part and the short term, long term, my part to part variation. If I'm even if I'm making this pen multiple time, there would be some variation from between my one pen and second pen and other pen. That's part to part variation. So all these things fall under SPC, which we will cover. And this, the second part, my measurement variation, this is driven through my MSA. So hope you are able to differentiate where my MSA is falling, where my SPC is falling. So I'm starting with MSA part. So when I talk about measurement variation, again it is split it into two categories. The first one is variation due to operators. So uh, different operator measuring some data, so that's part of reproducibility. We will cover what is reproducibility. And the other part is variation which are arising due to the gauge I am using, the operator, the aperture, the gauges which they are using. That could be because of the bias, stability, my linearity, repeatability. So these are the parameter which contributes, which falls under gauge parameter, and for operator, these are the reproducibility is the parameter. So this is the broad segregation of MSA and SPC. Now we will see these terms one by one. So when we are doing in our respective industry, how to capture bias, how to understand what is stability, what is linearity, what is repeatability, how to get that value, whether repeatability is there in my MSA or not. So all these we will cover one by one. The second parameter is why this error part. Why error come when we capture any part? Operator 1 is capturing the data, operator 2 is also again capturing the data. There is deviation. Why this deviation is coming? So again, this is split it into two broad categories. One is accuracy and other is precision. So when I talk about accuracy, this three elements fall under accuracy. These are my bias, stability, and linearity. And when I talk about precision, two parameters fall under this. The first one is repeatability and second is reproducibility. So if this broad skeleton is clear in our mind, let's move forward. If anybody has any question, the concern can ping me, the participant can ping me. I will try to answer. So let's read these things one by one. First one is accuracy, which we saw here. This one, accuracy, and second is precision. So I'm starting with accuracy first. So accuracy talks about closeness of mean of observed mean value to standard true value or reference value. So this is my reference value. The line which we can see, this is my reference value. Or I can say, like I said, the length of this pen is 10 centimeter. This is tested. This is 10 centimeter. So this is my reference value or true value, right? So if this is clear, so now read it again. Let's read it again. Closeness of mean of observed measure value to true value. So we are clear with true value, like this is true value. So true value, maybe we have manufactured 10 pens or 1000 pen and we got some average. We got some average that true value is my 10 centimeter. So this line, this vertical line represents my true value. Now the second is this part. If you see this graph, this graph is indicated my observed value. These are my observed value. These are all. So now what this first line is saying, you get the true value. For this case, pen case, this is 10 centimeter. This is true value. And second, I talked about the operator, the aperture is capturing the data and he will have different values, and out of those different values we calculated average of it, and the average value is this vertical line, right? Now what this accuracy is saying, you get the difference. you get this difference, which I have plotted here. This is my accuracy. Hope this is clear with everyone. So this is accuracy. Second point to accuracy is measurement system variation can be characterized by location. So here we can see this is one location. This is my location A with respect to my true value. And for my observed value, this is my location. So that's why it's written that measurement system variation can be characterized with location. So you see the true value, okay, it's falling here, and the captured value which I have captured and took average out of it, it's coming here. So location, you see the location spread, okay, how far these are. That also is the another way of saying accuracy. So it can, if I say how to improve it, if we do calibration, we can improve it. Now let's see what is precision. Precision is like we have captured data. Operator have captured data. Now he captured different data. He captured different data. Give me a second. Let me use another pen. So he captured data like this, one data, two data, three data, four data, like this. So you can also see that there is some spread between these data. It's not that he has captured here only. He has some different points. So what this precision is saying, the closeness of measured value, which you can see with the help of this graph, this green dots, green circle. So various operator have captured the data. So the closeness of data falls under precision. Hope you are able to make the difference between accuracy and precision. These are important terms in MSA, measurement system analysis. So precision is the degree to which instrument or process will repeat the same value. Make sense? So a operator is taking data with the help of vernier caliper or some other gauge. So is he able to get the same data or different data? This my precision is going to tell me, right? These green circles. This is so if I say my system is not precision, this system is not having high precision and all these things, then probably it's because of operator. Operator is not capturing the data properly. Maybe some training has to be given. All these things. Let's understand these word accuracy and precision with the help of example. If I see this A figure, this is not accurate, not precise. Why it's not accurate? Because this is my center. This is my center, and all data point which I have captured are away from my center. So it's not accurate. And why it's not precise? Because the operator have captured different data. It's not, these all data are not close to each other, which we can see. All these data points are far from each other. So it's neither accurate nor precise. And second, if I see the average data, these average data is falling close to my true value. My true value is center, so it's close to true value. So it's accurate, but it's not, again, it's not precise. Why? Because the operator have captured the data at a different point. He got different readings. So it's this B part is accurate but not precise. Third, C figure is saying my average is far from the center, which we can see. It's far from the center, not at the center, but the operator has captured data in a close vicinity. So we are saying it precise, but not accurate. And fourth, we can see all close to the center, just on the center, and all data operator which he has, the data which he has captured are close to each other. So the fourth D is both accurate and precise. Hope each one of you are able to make difference between accurate, precise. Very important in MSA. The next element to MSA is bias. So bias it also sometimes termed as accuracy. It talks about my true value, which I talked. This is my true value. This is my true value, and these are my observed value. This graph. So the gap between these, the difference between observed average measurement and the reference value is termed under bias. So a system, so when I talk about MSA, any measurement system, it should have least bias. It should have least bias. Otherwise, there will be some gap in the measurement system and it won't be able to capture my exact process variation. So it should be minimal. So, but it's again important to understand what is bias, how bias looks like in my system. And the other element to MSA is linearity. So linearity is saying the consistency of the measurement across the entire range of measuring gauge. So let's say, I'm interested to, I have produced I have produced various pieces from my CNC machine, and I, I also, apart from checking the quality parameters, now finally I'm checking the weight of it, and I'm checking system with my weighing machine. First I checked for 50 kg, then I check for 100 kgs, then I check for maybe 1000 kgs. So I am checking the variation which my system is giving, is that linear? Is the case coming with 50 kg, the variation coming is 1 kg, but with 1000 kg, the 1000 kg, the variation coming is maybe 50 kg. So then my system, so it has to be linear. So it talks about how the size of part affect linearity of the measurement system. So if I see this graph here, this green color, as my reference value is increasing, my observed value is also increasing. Both are proportionate, because this angle, if we say in a mathematical sense, this angle is 45-degree, so it's linear. So I'm saying no bias and my system is linear. But in second case, it's not proportionate, it's biased. The change in my reference value is not proportionate to my observed average value. So I have to make sure that my system, if I'm capturing data, my process has to be linear throughout the range. If that weighing machine is able to measure the weight between 50 kg and 1000 kg, so it should be linear between 50 kg and 1000 kg. There should not be deviation between 50 kg or any of the weight in between, maybe 1000 kg, 500 kg, 100 kg. If there is deviation, then I will say my measurement system is not linear. I need to check in that case. The other element in measurement system analysis is stability. So why this stability is important? So I'm capturing the data, right? So today I captured the data. I got 10 centimeter as the reading. So again, after 1 month, or maybe after 6 months, or after 10 days, I captured the reading. But the same operator got the data 10.2 centimeter instead of 10.0 centimeter. So stability says whether time is changing or not, the reading should not change. If it's changing, this means that over a period of time, my system is not stable. And this is a matter of concern for me. So probably we have to look back. So let's see all these points one by one. Instability. A measurement system is stable if there is no spatial cause variation affecting the measurement system bias over the time. So one word I have used, spatial cause. Special cause is a sort of cause which usually doesn't occur, but if happen, of a sudden. So if I give you an example, the one is my common cause, which are a normal causes which keeps on happening. See, if I am producing a piece, there will be vibration in the machine, some vibration in the machine. That's my common cause. But of a sudden one day what happened, machine start vibrating a lot, and because of which it came into breakdown and pieces, I got defective piece. That's a special cause. That's a special cause, why machine had that extraordinary vibration on that day. Maybe something came in between the machine. That could be the special cause. So if that special cause is coming in the machine, or in is affecting our part, then our reading will not be stable. Then I will say I am not having the stable system. The second element to it, stability refers to capacity of measurement system to produce the same value over time when measuring the same sample. As I said, I captured the data. Initially, it was 10 centimeter, and next time I got 10.1, 10.2. So if my process, if my system is not capable to get that data, same data, 10 centimeter in this case, again and again, then I will say my system is not stable. Means I am the MSA, there is some gap in my MSA because of some stability issue. So I need to check. So in that case, I need to check why stability is breaching, why stability is not coming. Because if I keep on doing even with unstable system, then I will get the wrong reading. The exact was 10, but I was getting 10.1, 10.2, and probably when this data will go to the next level, statistic process, SP statistic process control, and all these things, and goes to the customer, this part is going to get rejected, and there would be a loss. So MSA is the stage where we need to control. So third element is variation in the measurement when the same person measure the same unit using the same measuring gauge over the extended period of time. So here we can see this is my time 0. Again, this is time equal to t1, let's say. So some gap has started arising. So initially there was no gap with respect to true value. So when I am saying gap, this is with respect to true value. I know the dimension is 10 centimeter. Its length is 10 centimeter. So when at t equal to t1 this data has been captured, this gap has increased, bias has increased. So I'm saying over the period of time, this my system is not showing me the stability conditions. And again, when I am going to time equal to t2, which is probably where t1 t2 is greater than t1, so I am seeing this gap has further increased. So my stability, I am breaching stability. So with this figure I can see that. So need to control. So MSA help me controlling these elements. The next is gauge repeatability, which these are repeatability and reproducibility. These are part of precision, which I shown it in couple of slides back. So gauge repeatability talks about it is a measure of how consistently the same person measure the same event over the time using the same measurement system. So it's saying that we have same set of people. We can see these are same set of people, or we can say people or operator, same set of people. This is one thing. These are capturing, so same person. So first key away is same person, same, and second is same event. So same event means if you are measuring if you are capturing the reading of this pen, length of the pen, the event will remain the same. You can't change from this pen to this cylinder. You can't do. So that's a event. So the operator, same set of operator and same set of event, means same set of part, and this is second. So 1 second, and third is my gauge. So it's not that if you are reading the length, if you are interested in taking the length of the pen, you are initially doing with vernier caliper, now doing with scale or some other measuring instrument. Can't do. So my measuring instrument will also remain the same. So if I am able to do these transactions again and again, and I get the same value, try to understand. If I am able to do, which in manufacturing company we always does, if we are involving same people, same part, or I can say same event with same set of gauges, and I am getting the same reading, those people, those gauges are able to get same readings, then I will say my this system is my I have gauge repeatability. It's that the system is able to repeat the value again, which is good, which we really want. So this is the meaning of repeatability. The second is gauge reproducibility. So here the only difference is between repeatability and reproducibility is this. Here my operators are not fixed. You can see these are different operators. Maybe the male with respect to female or any of the operator. Uh, the operators are different. Give me a second, please. Yeah. So here the operators are different, and the part which I am measuring in pen in this case will remain the same. The gauge will remain the same. This will not going to change. So this gauge reproducibility is saying if with this set of parameters, if I am able to get the same set of values, 10 centimeter in this case, all the time, again and again, then I can say my MSA, my system is gauge reproducibility. I am able to reproduce the same result again and again, because for the same piece, it should be same. So imagine the scenario. You are producing the same pens of 10 centimeter, but different people are coming, different operators are coming, appraisers are coming. Few are saying 10.1, other are saying 9.9, few are saying 10.2. But means different readings they are getting. Now this MSA is going to tell me if I am getting different reading, would I be able to accept that data or not? Can that fall under reproducibility or not? Because just by reading this thing, we cannot say my system is reproducibility or having repeatability or not. At the end of the day, we have to rely on data, because when we are capturing data, few I will also brief how to capture data in this. So when we capture the data, finally we get some value. So we see that value, and based on that single value, we decide whether to accept this data or not, whether this data is into acceptance limit or not, whether to accept it or reject it. So whenever we do MSA, we have different types of data. One is continuous, which we also call variable data, and another is my attribute data. So continuous data is that which I talked about, where data comes, some values come, 10, 10.1. In this example, if I say length of the pipe, length of the pipe, so length of the pipe, it can have different reading. If I am a pipe manufacturer, it could be 500 meter, it could be 500. If I start measuring, it could be 500.1, it could be 500.5. So these are my continuous data. So continuous data can hold any value. That's continuous data. Second is weight of milk packet. So if I measure a milk packet, there will be some variation in the weight. So again, part of my continuous data, variable data. So we use test as gauge RNR crossed in this. And for the second parameter, attribute data, it's talk about, if I have to, let me give you an example. If I'm interested in knowing whether this piece has been accepted or rejected. So I simply put data like part 1 accepted, yes. Part 2 accepted, no. It could be, instead of y, we can also write 1 or anything, any number we can also assign like this. So these sort of categories will fall under my attribute data. If I am saying, I am making CNC part and I am saying whether there is scratch in that piece or not. So if there is scratch, I reject it. If there is no scratch, I accept it. So if I am making the demarcation with respect to scratch, that will be part of my attribute data. But for the same piece, if I am making the demarcation with let's say length undersize or oversize, and I am writing the data, I am not saying just undersize or oversize, I am capturing the data, it's 5.1, it's 5.11, something like that. Then the same piece will fall under my continuous data range, variable data range. So in that, my MSA study will be different, gauge RNR crossed, and in if I'm using this scratch and this attribute part sort of thing, then it will be attribute RNR. So I have given you the example for one piece only, CNC piece. The type depending on my requirement, I have, the same piece can fall under my continuous and attribute. But one thing I would like to share, advisable to have, continuous data scale. Whenever possible, go with continuous, because continuous is about data. It's about real-time data. Attribute will not quantify, the level of scratch. It will only say there was some scratch, right? But this continuous data, when I'm saying undersize oversize, if I'm giving you the data, then it will also say if it's undersized, by how much, by what measurement it was it was because of 1 mm undersize, it was maybe because of 3 mm or 4 mm. So the level of severity my continuous data will give, attribute will not give. So we have to select this thing wisely, how to which one to select, continuous or attribute. So let's quickly see how to conduct gauge R&R, variable study. So here we have couple of requirements are needed. First, we need minimum 3 operators. First operator, Ram, Syam and Ghanshyam, let's say. These are 3 different operators. And I need 10 distinct part. If I'm interested in capturing the variation in the pen, I need minimum 10 pens. Not only 10 pen, one more parameter to it. It's not that you get just 10 pens which are all are into good specification, into the specification LSL and USL or defined by the customer. It's not that. These 10 pen should be randomly selected. randomly selected from the pool, or it should have data which fall which are into the rejected category also. So that should be, then only we would be able to know whether the operator which is capturing, maybe all the time he is saying my piece is good and my piece was actually good, that's why he was saying good piece. So it should have all the variation, it should be spread it across the entire range. That's why written all part variation. It's important. And third is minimum 3 readings. So I need 3 operator, Ram, Syam, Ghanshyam. Hypothetically, I'm giving the name, and 10 distinct part with wide variation. Second element. Third thing, the same pen, the same pen should be captured by one operator, single operator, minimum 3 number of times. So if I see this data, so the total number of data points will be 3 into 10. 3 are my operators. These 10 are my distinct parts into 3. These are my minimum readings. So I am writing minimum values. It can be more. 3 you can replace 3 by 5. So I am writing the minimum value. So if you calculate this, it will be 90. 90 readings. Hope all of you are with me. So there will be 90 readings, right? So when we have to check, so I'm telling you common both for variable and my attribute, because the logic remains the same. In attribute, probably we have to capture more data. Instead of 10, we need 30 data points, but the logic of capturing the data and analysis, that somehow remains the same. So when we are done with this 90 readings, so we ask operator to come. We ask operator, so we make a chart, that piece 1, the true value is this. Let's see what's the reading coming out from the operator, from my appraiser. So we ask, let's say Ram first, and ask him uh, to capture all these 10 readings, and these part will be randomly given to him. It's not that part 1, part 2, part 3 and up to part 10. It will not be in a sequence, it will be randomly arranged and given to him. He captures the data, then Syam comes, second operator. Again, these readings are jumbled and these parts are jumbled. He captures the data, take the reading. Now third operator is being asked. He captures the data. He takes the 10 readings. Then again, uh, first operator come for its second trial. For the second trial, if you can see, minimum 3 readings. So it's not that you call Ram and he captures 3 data in one go. Not allowed. So in second attempt when he comes, again data is jumbled. The parts are jumbled. He won't be able to know whether he has taken part 1 or part 2. Otherwise, he could do some cheating. There could be some biasness in his opinion. He will say, last time I have given this value 5.1 to this reading, I should again give 5.1. So he captures data. He again captures data, and again second operator is asked, and third, and then after that third trial is done. And this way all 90 data are being captured, and then the analysis part comes. Hope the logic of capturing data is clear with everyone, because I have seen in companies people know little bit about MSA, but they are very much confused how to capture data, what the sequence that should be adopted for capturing it. So this is the formula, this is the rule book for that. So thumb rule for my ANOVA method. So when I'm saying, this gauge RNR, this for continuous data, one of the method is ANOVA, which is most popularly used. Another are my range method, and the second is range and average method, which are not very frequently used. So this is the method which is most frequently used. That's why I have mentioned this only in my slide. So as a thumb rule, if the value is coming less than 10%, this R&R, repeatability and reproducibility we know. So if this value is less than 10%, we accept our measurement system. We accept that and we can go to the next level, that is statistical process control, SPC. But the second scenario, when this R&R is between 10 and 30, then I am not saying you accept it, I am not saying you reject it. Based on the confidence, it could be accepted, it could be rejected. So you make a decision based on classification of characteristic, application, customer input. So based on the your data from the customer, from your production team, you decide whether this data can be accepted or not. And probably if you are accepting in this time, you have to improve it so that you fall under this bracket, less than 10%. And if this scenario is coming, third scenario, R and R over 30%, more, which is more than 30%, then there is simple rule, you cannot accept it. If you accept it, you are probably capturing all wrong data. Your operator are not trained. You cannot go to SPC. A big blunder one will do if one will capture R&R over 30%, if that data is going to be accepted. So we have to find problem, we have to do fishbone remove, we have to do root cause, and we also have to incur additional cost, because we have done so much exercise and we came to know our measurement system was not capable. We have to improve it further. So we have to do the complete exercise again and improve our measurement system. But at the same time, this is also important to get the data. If we not get this data, if we don't do MSA, we won't get the data whether we are at number 1, number 2 or number 3. We will consider number 3 as number 1, and we will jump to SPC. That will be a big blunder. So it's important to do MSA, and accordingly train our resources, accordingly do calibration of our gauges, so that we can fall under this case 1, first parameter. So we talked about this first element, the continuous scale. Now the another one is attribute. So attribute agreement, in this what happens? So we talk about attribute data. So I gave you the example, scratch, no scratch, 1, 0. I did visual inspection, and the product is going to be accepted or not. Those sort of data you put when doing attribute agreement, attribute type of MSA. So attribute data, it's a qualitative in nature. It's go and not go. This, if this piece is going, I accept it. If it's not going, I cannot accept it. So that's part of my attribute. So attribute measurement system, a measurement system that compare each part to a standard and accept that part if the standard is met. So the same thing which we did in continuous, we have our standard, which we call it true value, or we have seen reference value. With respect to that, so first, when I'm doing attribute, I capture the true values. So true values will be captured by my quality head, or the person who is trained, who knows how to get the data. So he captured the value and he says, yes, this is my true value, this is my master value, this is my reference value. And corresponding to that, my operators are being asked, now you capture the data, and we will compare whether our measurement, whether the true value and the observed value are same or not. If these values are not same, whether my MSA is going to accept it or not. If let's say I have captured 1,000 data points and one data is wrong out of it, means operator, the master has said, the quality has said no scratch, and my operator has said yes, there was scratch, so there is gap. So out of 1,000 data, if there is one data which is, where operator has said no scratch, so there comes a point where, just by seeing these values, we cannot decide whether my MSA, we can go with the this MSA or not, whether we need improvement or not. So we get data. So based on those readings, we get data, and with the data, like we did in continuous scale, we decided. So similar practice we adopt in attribute also. So this further says select 30 or more parts from the process. So one must be wondering, in continuous, in variable scale, previous one, we took 10 or more parts. But here it's saying 30 or more part. Why it's more? Why it's more? So the reason is attribute, as I said, continuous is more powerful technique as compared to attribute, because in attribute we are capturing data like scratch, no scratch, okay, not okay. So we need more pool of data to have the same level of confidence. That's why we are capturing more data. Instead of 10, we are capturing 30 or more to get some meaningful information out of it. If possible, select borderline or marginal good and bad samples. So here, let's say, this is one scratch. This is one scratch, right? Another scratch, because this is for attribute, so I'm giving you example with respect to attribute. So for operator, the one operator has said yes, there was scratch, and another part is having, CNC part is having this much scratch, only this much scratch, and third part is having this much scratch. Now in this, operator is saying this is acceptable, and here also in third piece, operator is saying there is scratch. So idea is that we need to check whether my operator knows what is the boundary for my scratch. See, even a layman will say this is scratch, no big deal. Here confusion come. So it's written select borderline or marginal good or bad samples. So I have to select all the samples, maximum possible sample, which are having big scratch, very small scratch, and which operator will also think, whether to accept it or not. So we are interested in knowing that if that operator is good enough to decide everything as per the, the true value, means the quality head has said, okay, this is will be treated as no scratch. If the operator is saying the same thing, this means operator is good enough. He is able to have that reproducibility part. But if that is not happening, then probably we have to give him training and all those things. So when doing attribute agreement analysis or my variable, I have to have all set of data, all set of parts to get the full variation in my process itself. Select inspectors fully trained and qualified. This is important. Otherwise, what will happen? We keep on spending a good amount of time, capturing the data. We saw that example, 90 readings being captured. So each person was called one by one after another. So it could be 5 hours, 6 hours job. So if my people are not trained to do all those things, probably what will happen? I will, end up wasting my 6-7 hours. So better we don't commit mistake at our end knowingly. And the third is execution. Each inspector inspect the part in random order to determine pass or fail. Like here we did, it's pass or fail, okay, not okay, pass or fail. Each inspector repeats the inspection or trial. So this was trial, first trial, second trial, third trial. So these are the steps involved in my attribute agreement analysis. So, like in continuous, we use some data. Like if it's less than 10%, we accept it. In attribute, we generally use the kappa word. If my kappa is, the kappa is calculated with this formula. So the ultimate aim is to achieve kappa value close to 1. If I am getting close to 1, this means it's 100% agreement between my appraiser means operator, and reference value. Reference value means the quality head or the master who has said, okay, this is scratch. This is having scratch. So operator and master and reference value are same. If in all cases these values are same, my kappa value will be 1. In second case, if it's greater than 0.75, we will accept that. And if it's between 0.5 and 0.75, so measurement system is conditionally accept. The same case which we saw in conditional part when it was less than 30 and between 10 and 30. So that was conditionally accepted. And if kappa is less than 0.4, we cannot accept my measurement system. So it's a matter of concern for us. So based on the type of data we capture, we have to see the matrix accordingly. So properties of good measurement system. So good measurement system says that my process, if I am using vernier caliper, and my customer has given me the tolerance of, let's say, 50 plus minus 0.5 mm. So this 10 to 1 rule, adequate sensitivity, means that my process is able to capture at least 10 readings of the tolerance of my process variation. So here we can see my uh, this will be 49.5, between 49.5 and 50.5. So my tolerance is 1 mm. So if I use, let's say, vernier caliper in this case, vernier caliper would be able to give me 10 readings corresponding to 1 mm, 1 mm deviation. So I have to use my gauge accordingly. So we call it 10 to 1 rule. So adequate sensitivity of measurement instrument is required. Let's say I use scale here. What will happen? It will give me reading with respect to mm, 1 mm, 2 mm. It won't be able to capture that deviation, and my purpose will not be solved. And second part is instrument accuracy should be able to divide process variation into 10 distinct parts. So we saw with the help of vernier caliper, it was able to divide into 10 part, 10 distinct units, 10 distinct part it was able to split. So least count of the instrument measurement system should be able to divide process variation into 10 or more part. That's my least count. The measuring instrument should be sensitive to process variation. So we saw that vernier caliper was sensitive. For 1 mm tolerance, it was able to divide into 10 parts. Process is in statistical control, which we will see in coming slide. What is statistical control and all. System to have common cause, not special cause. We will again see in SPC. Second element is statistical process control. So we talked about MSA, measurement system analysis. So once we are done with MSA and we have accepted our system, that MSA values are within the acceptable limit. Once that is done, then only we can do statistical process control, because statistical process control is talking about that variation. I showed it in the last example, you know, that this variation 50 plus minus 0.5 mm. When my measurement system is capable to capture that deviation properly into distinct part, then only I would be able to do SPC, statistical process control. We will see what is SPC. So it is method of monitoring and detecting changes in the process. So over a period of time, what happens? My process keeps on changing. My process keeps on changing. If I give you an example, if a patient is admitted to a hospital, let's say he met with surgery and all these things, and doctor put, you know, we must have seen in TV and in real life also, doctor and nurse, these put some, you know, instrument on the body which captures its real time data, you know, blood pressure data, if it comes ECG, small monitor, we keeps on and you know, nurse and all those things keep on monitoring those data. And we must have seen in TV and all these, this data is never straight. This data will not come, you know, different monitor will not say data like this, it shows data like this, right? It shows data like this. So means this data is also deviating up and down, some motion is there. But this range is acceptable. If my BP is fluctuating, that fluctuation is okay. But there are some limits. But now comes the main thing. There are some limits. If I cross those limits, then it's a matter of concern. And I say my process is not into statistical control. So I use the word limit. Here limit are my lower control limit and upper control limit. So if my data is going beyond, if my graph is breaching those levels, upper control and lower control, probably budget start ringing, you know, from that room, and sister or doctor start running to that patient. What happened? What happened? There is some matter of concern. So that's why it written method of monitoring and detecting changes in the process. It's monitoring the graph and detecting the changes, not doing anything. But that is also doing very important, you know, in 26 January, you know, police, you know, doing surveillance. They are monitoring and detecting is any, you know, unwanted thing coming. That is also very important. Same thing SPC is doing. Before any culprit come into picture, before any deviation come into picture, the police or this process want to capture that deviation. That's why, you know, monitoring and detecting is being done. That's about SPC. So it's used to check whether process has changed over a period of time, so that we know over a period of time my process is going to have that drift, that stability part and all those things. So I'm checking as of now whether is this process within my control or not. So if I talk about any manufacturing process, you know, or some recruitment process, so there could be a case, you know, I hire a HR person, or I hire a quality person. This time I took just 2 days to hire, and the next time when HR hired the quality person, the another quality person, he or she took uh, not 2 days, 10 days. So there is some deviation. So probably from the management, the voice was, we want within 7 days. So then this means my process is not into control. If I talk about manufacturing, I have some control limits. And if it's going beyond that, this means matter of concern, I need to control my process. So what this SPC is doing, so it helps us to identify and analyze the source of variation. We will see how it captures the source of variation and reduce part to part variation. If you remember, initially I showed you one diagram where, you know, it was split it into, one was the right side was toward MSA and the left was toward SPC, which was, you know, short term variation, my long term variation, and part to part variation. So this we are capturing now, part to part variation. Let's see with the help. So the statistical process control uses control chart to control the process. So there are some parameters in my SPC or control chart which we need to understand before going forward. We will go one by one. A statistical process control tool to determine if my process is in state of control or not. So what I have to do, in there are various type of control chart. So based on control chart, we see whether my process is in control or not. This is my process. This is my process. And this red dash, these red dashes are my control limit. These are different from my specification limit, the customer specification USL and LSL. That USL and LSL come from the customer. Customer says, I want this much tolerance. That will be part of my specification limit. But here I'm talking about UCL. Please don't get confused with, don't mix specification with control limit. So this control limit are calculated with the help of formulas and all. Formulas we are not discussing today. So these with the type of data which we get. So based on that, we automatically get these lines. We automatically get these lines, and if the process data are coming within these lines, within these USL and my LCL, then I say my process is in state of control. My process is stable. This is my first point, is in state of control. Second point, it's saying a control chart has a central line for average. So this is a central line. We also call it average. As this is center, so we also call it average, and these are my, as I said, upper and lower control limit. So when this is calculated, formula is fitted in such a manner that these control limit are 3 sigma. We can see from here 3 sigma deviation from the center line. This is my center line. So this is plus 3 sigma and this is minus 3 sigma. And the last point is a process statistics such as subgroup mean, range, standard deviation, individual observation are plotted versus sample number or time. So here if we see the x-axis, we usually put time like 11 o'clock we captured the data, now 12 o'clock, or maybe shift 1, shift 2, maybe date, like this time parameter will come, time, day, date, or number could be with respect to I'm into a milk factory and I have captured 10 pieces, 10 pieces of milk I have taken. So with respect to 10 pieces, with respect to 20 pieces of milk packet, for 50 pieces, 100 pieces. So these all will be part of my x-axis. So we have to decide accordingly what's my requirement. And in my y-axis, which is written with characteristic, these many parameters can come. It can have mean. Mean we know it's sum of the values divided by the number of reading. That's my mean. It could be range. Range we know it's if my data is like then my range is, this is my minimum value, this is my maximum value. So minimum, maximum minus minimum will give me the value as 8. That will be my range. Standard deviation, that's a big formula. So standard deviation, it says about the spread between data. If I'm using more number of data, so in that case, we are more interested of spread. Spread means how far my data are deviating from each other. That's typically calculated with the help of standard deviation, spread. So if required, we use this parameter in y-axis or individual observations. So we have to decide based on the type of chart, whether we are using the number of data, whether we are using 2 data, 3 data. I will give you I will share how to when to take range, when to take mean, when to take standard deviation. There is formula for that. I will share that. The process control is inherent to process characteristic as against process capability, which is measured as per outside target and specification. The next one is purpose of control chart. Why we need control chart? So there are two elements to it. If you see it, one is common cause variation. Other is spatial cause variation. So common cause variation means my natural variation, which is within the system. I gave you one example. If you are using a machine, there will be some vibration. There will be some vibration within the machine, which probably cannot be reduced. So these are my natural variation. We also call it inherent in my process. Also call it white noise or non-assignable causes. We cannot assign any region to it. Why that vibration is coming? If I talk about any element, there will be some protons, atoms, and in this, and atoms we know they have zigzag movement. So I cannot say the atom 1 will have movement, zigzag movement like this, atom 2 will have movement like this, atom 3 will have like this. It adopts random random motion. So that's why it's part of my common cause, which is common. These are common, which happens, which will happen, and we can't ignore. And we are even not concerned about common cause, because common cause as such is not hampering the MSA or not hampering the output as such. The thing which we are concerned, the variation which we are concerned, is spatial cause variation, because this is the real culprit. It's assignable. Something has come inside the machine and my product failed to get the right set of specification. So that is my spatial cause, and that's why it said it's assignable cause. You can say with full confidence, full assurity, why this breakdown came, why this thing happened. A person coming late by 1 minute, he probably won't be able to give any proper reason. But a person coming late for more than 1 hour, beyond 1 hour, he must be having some reason to it. That's a special cause, because nobody will come late after 1 hour. This training started at 11. Most of the people, majority will fall under the common cause. Few joined at 10:55, 11:05, 11:04. But if there is a person who joined at 12 or maybe 12:15, that will be part of special cause. He must be having some specific reason. He must be having specific reason why he joined so late. Yeah, so we can assign cause to it. So spatial cause are also called black noise or variable outside historical data. So this is the chart I was talking about, like how to make segregation, how to decide which type of control chart we have to use when. So when my data, the first thing is when my data is continuous. So my data could be continuous, my data could be attribute or discrete. So here first I'm starting with continuous or variable. So the case could be my individual data point. I am taking one data at a time. Maybe one milk packet I am taking at one time, not two. So these are called individual data point, pulling one sample at a fixed frequency. It could be subgroup. Subgroup means you are not taking one data at a time, more than one data at a time. Maybe you are not capturing one milk packet, you are interested in capturing two or more than two milk packet at a time. That will fall under subgroup. For individual data points, we use INMR control chart. So variability of individual characteristic over time. And for subgroup, if my range, if my data points are less than 9, means the at one time I am taking less than 9 data, I use X bar and R, mean and range chart. But if I am using data more than 9, so I am using mean X bar and S, mean and standard deviation chart. So why for more I am using standard deviation? The reason is, if when my data increases, I am more interested in the spread of the data. I'm just not interested in range. Range will simply do maximum minus minimum. But when data are more, I'm overall interested in their spread. So that's why I use X bar and S. That's the part of continuous. And the other is my discrete data. Discrete data is further divided into my defective and defect. First we have to segregate between defective and defect. So if I say CNC piece, if um, if it's having let's give you another example. Let's say I'm some doing some questionnaire, mobile testing. So my mobile could have various defects. My mobile could have various defects. It could be maybe my screen is broken, maybe capacitor is not working, maybe battery is not operational. So these all are defect type, defect 1, defect 2, defect 3. If I am capturing data in defect type, if in CNC, if I am saying length oversize, my bore oversize, and all these are my defect type. So because of one defect, it could be, it can lead to defective. And defective means my overall piece is not acceptable to the client. I am saying the entire lot is defective, not accepted. That is defective. So again, my defective is divided into constant subgroup size when I am drawing the same number of samples at a time, one case. Second could be I am drawing varying sample, one time I am taking 2 samples at a time. After one I have 3 samples, then 10 samples. I am changing the frequency. So then it's varying subgroup size. So for constant, I use NP chart. For varying, I use P chart. And for defects, if it's constant, we use constant subgroup size. Another is varying subgroup size. The logic remains the same. If my subgroup size is constant, it fall under constant. If I am drawing varying samples, change sample, 2 samples, 10 sample, 15 samples, then it will be fall under varying. And the chart we will use is C chart and U chart. The initial logic of control chart I have given, the logic applied is same. The only thing, if we can get the logic of each part, we can easily decide which chart to use. Minitab does this thing automatically for us. We just have to punch the data and give the command, go to NP chart, P chart, it gives the data. The understanding of selecting the type of chart is more important. Let's have a couple of differences between MSA and SPC. So MSA talks about, to check whether measurement system variability is small compared with the process variability. So it's saying whether I'm going to accept my data or not. A second point of MSA is whether measurement system is capable of distinguishing between different parts. That least count I'm talking about, whether it's able to distinguish, into 10 parts, into 10 distinct part or not. MSA talks about that. Whereas SPC talks about to establish a control manufacturing process by the use of statistical technique to reduce process variation. As we saw with the help of control chart also, and in SPC, it tell you, that my data is drifting, you control the process. So it's more about controlling the manufacturing process, whereas MSA is about whether my system is capable to capture data or not. Do I need to do some changes? MSA talks about this. The second is to monitor the performance of measurement system. So measurement system includes, my operator, gauges, my process, all those things. So it's saying whether my measurement system is good enough or not. Performance is checking. But my SPC is checking the performance, to monitor the performance of the measurement system, to identify the variation in the process due to standard, workpiece, instrument, person, instrument. So we also call it swipe. So it is going to tell me how my standard is there, workpiece, my instrument, person, equipment, how these parameters are performing. MSA will going to tell me. Whereas SPC will tell me, it talks about my common cause, my spatial cause. The key input for MSA is my gauge R&R. We saw it. For continuous we use gauge R&R. For other we use other type of tool attribute. So for SPC, the key output is my process capability, CP and CPK. It talks about this whether my process is stable or not, process is capable of performing or not. In MSA, it is requirement before conducting a SPC study. So whenever we do SPC, it's important to understand we have to start with MSA, measurement system analysis. Then we can jump to MSA, if SPC. If we directly do SPC, then we will start getting the wrong data, and customer, we will surely have escalation from the customer, and we will have rejected pieces as well. So we have to be careful on this part. In MSA, major variation present in all type of measuring instrument and test equipment. So my measuring instrument, my gauges, my inspection method, in process method, my outgoing. So all those things is part of my MSA. Whereas my SPC talks about my critical to quality. Critical to quality means all those parameters which are important to the customer. All those things will be captured here. And it's in MSA is major possible bias from operator, instrument, method. So MSA, once we are done with MSA, we would be able to know, whether we have to give training to my operator, whether I have to do calibration and all those things. That will fall in the MSA. And SPC, the aim is not to allow defects to be produced. So it talks that we should not get defect. That's why, that control chart we use. Whenever anything is going beyond, we control it. So these are few differences between MSA and SPC. Hope these things are clear, and that's all from my side. Any questions from any of the participant, please? Yeah.
Thank you, sir. Thank you so much for the wonderful session.
Thank you.
Sir, we have received in the chat box. Sir, one question from Guru Sridhar. How do you set the control limits for a new processes?
See, very good question. What happens in we capture the data initially for a new process, we also capture the data, and once we start capturing the data, we put that into the control limit formula, and in control limit formula, this control limit is going to tell me for my process, whatever I am manufacturing or services I am providing, is that the thing which I am producing is within some limit or not. So that limit will automatically get calculated by the formula. It's not that we set the formula, the formula automatically draw that line, lower control and upper control. It plots, and then we have to check the data range whether it's falling within or not. Even for new, the logic remains the same. And at times, we also use historical data to get the control limit for us. Yeah. Hope I am able to answer your question. Any more questions, please?
Ashish, you're not audible.
Wait.
I'll read out the questions. Next question is from Mr. Kiran. Can you demonstrate MSA method is to be used for destructive samples in bulk production, not part production?
Can you repeat, please?
Can you demonstrate MSA method is to be used for destructive samples in bulk production, not part production?
Yeah. See, so whenever we use MSA, the idea is to get the data which we are capturing with the help of our operator, and with the help of the gauge, whether I am using destructive testing like we use for bulb, to check whether what pressure or what heat it can withstand. So I again use the same logic. I check the data which operator is capturing with the help of set of gauges. The data which is capturing, is that part of my MSA, is that solving my requirement. um, Once I get that continuous data or attribute data, I fit it into my formula and check whether that's coming into the specification. So even for destructive testing, that the logic for capturing the data remains the same. Yeah.
Okay, next question is from Ms. Kavita. When the product is part of any particular machine, then the length will be continuous data or attribute data?
When it's part of the process. See, length we usually count under continuous data, because when I am manufacturing any pen or any pipe or anything, there could be some variation. So it fall under continuous scale.
Okay. Next is from Mr. Anupam Kumar Rai. What if pen is having variation on OD from top to bottom? How we can reduce the variation?
Yeah, very good question. See, first, if variation is coming, we have to check. First, we have to take customer voice, and which we have taken in this. So after taking capturing the customer voice, the second thing is that we came to know that okay, my MSA is robust enough, but I am getting this OD problem in my pen or in my piece. Then I have to do that root cause analysis, that lean methodology I have to apply, lean tools I have to apply, that root cause analysis, brainstorming, Pareto, all these things I have to apply to drill down from, like, if this is the problem, what is the root cause? How to cut it? So MSA is just going to give me the clarity whether the operator, the gauge which I am using are good enough or not, whether I can continue with this or not. The problems which are falling is not part of MSA. It's part of some root cause analysis tools and all those things. So this will be a different ball game altogether. So MSA talks about this only. Yeah.
Okay, next question is from Mr. Vinod Kumar. Difference between least count and resolution?
More or less these are same. Least count talks about if I'm using vernier caliper, I'm taking the reading of with respect to millimeter. So we know this vernier caliper can split it into 10 pieces. So least count would be my 100 micron in that case. And resolution is the part up to which it is able to resolve it is able to distinguish between different pieces. So both are used in a same manner.
Okay, next question is from Mr. Star. How uncertainty of measurement is related to MSA?
Uncertainty of measurement. See, in MSA, what we are doing, we are capturing the data with the help of gauge, operator, and all. So once we are capturing the data, we are checking whether it's falling within the acceptable limit or not. So if it's falling under the acceptable limit, like we saw in the continuous, if it's less than 10%, we accept it. So if it's accept, we accept the data. Yeah.
Due to paucity of time, we cannot take up all the questions, but you may write your questions to us and to Mr. Amit Kumar, and we will answer your questions over an email. Thank you so much. Ashish, would you like to close the training
Yes,
program?
ma'am.
Yeah, thank you.
Sure, ma'am. Thank you, ma'am. Before we end this program, on behalf of NBQP QCI, I would like to extend my sincere thanks to our speaker, Mr. Amit Kumar, for sharing the informative session. I hope it was useful and informative to all. Once again, thanks to all the participants for interactive session. We would be sharing feedback form with you. Request everyone to spare some time and give us the feedback, as your feedback is valuable to us. Thank you so much. And I would request you to please switch on your webcam so we can take the group photograph. Sir, please unshare your screen.
Yeah. Is it done?
Wait, sir. Yes, sir, it's done. Requesting everyone to please switch on their webcam.